Great. Good afternoon, everyone. I am Dr. Tarak Karmukar, an assistant professor in the Department of Chemistry, IIT Delhi. I welcome you all to the eighth lecture of the Sci-Tech Spin series, an academic outreach program organized by Indian Institute of Technology, Delhi. The purpose of this monthly lecture series is to connect to the young minds of our country, introduce them to the world of scientific discovery and state-of-the-art technology. Today we have with us Professor Yama, who is an assistant professor at the Center for Atmospheric Sciences at IIT Delhi. A little bit of background of Professor Dixit. Professor Dixit received her PhD degree from University of Cambridge, UK. Afterwards, she moved to France for her postdoctoral research, and then she moved to Singapore for her second postdoctoral research, and then she joined IIT Delhi as an assistant professor in October last year. Her broad area of research is on understanding the pattern and mechanisms of climate change by using experiments in lake or ocean sediments. In particular, she is interested in Indian monsoon variability, impact of western lines on Mediterranean climate, South American monsoon variability, and its impact on Amazon River runoff. So the topic of today's talk needs no introduction. I mean, we always talk about global warming and how it impacts the variability of monsoon across the globe, and of course other consequences, and how we can learn from the past and understand, rather predict the future climate changes. So today's talk, learning from the past, climate and civilization changes. So a bit of technical details. Along with the WebEx platform, we are live on YouTube. So you can post your questions either or on both places. The speaker will try to answer a few questions during the talk, and the rest of the questions will be taken by the speaker at the end of this lecture. And I think we're going to have a question answer session. With this little introduction, I'd like to invite Professor Dixit to share your slides and start the lecture. Thank you. Over to you, Professor Dixit.
Thank you, Tarak, for the introduction and for giving me this opportunity to interact with school students and young minds. So I'll just share my screen. Hello, students. I'll be talking about something that you see on the title, Learning from the Past, Climate and Civilization Changes. So the title is really interesting because like when I was reading it, I was thinking, is it going to be a science talk, or is it a history talk, or is it an archaeology talk, or is it like, what is it? What is it going to be about? So I think Professor Karmakar did introduce me as to what I did for my PhD, but I really want to let you know what I did after my school, which kind of enabled me to do this kind of research, which I'll show you in a bit. Now, after my school, I came to Delhi for the BSc Chemistry Honors degree. And then I moved from chemistry. So my undergrad and my basic training is as chemist. Now, I liked how chemistry is being applied to environment. And then I moved to JNU, Jawaharlal Nehru University, to do environmental sciences masters. And then I moved to Cambridge for my PhD and so on, continued research in this field. So that's my background. So that gives you sort of an idea of what all disciplines that are going to be discussed here when I talk about past climate and civilization changes. Now, it's a Saturday afternoon, and I was just thinking, like, if I were a student, I would rather be watching a movie, on a Saturday afternoon. Now, I've been given this task that I should talk about research, but then I would still like to show you a trailer of a movie, which is very interesting. And this is a trailer. You should go watch it. It's a documentary movie, but really relevant and really interesting. So, yeah, there you go.
If you look at the 10 hottest years ever measured They've all occurred in the last 14 years, and the hottest of all was 2005. Sign of warming. I am Al Gore. I used to be the next president of the United States of America. This is Patagonia, 75 years ago, and the same glacier today. This is Mount Kilimanjaro, 30 years ago, and last year. Within the decade, there will be no more snows of Kilimanjaro. This is really not a political issue so much as a moral issue. Temperature increases are taking place all over the world, and that's causing stronger storms.
This is the biggest crisis in the history of this country.
Early this morning, Hurricane Katrina slammed into New Orleans.
Is it possible that we should prepare against other threats besides terrorists?
From Paramount Classics.
The Arctic is experiencing faster melting. If this were to go, sea level worldwide would go up 20 feet. This is what would happen in Florida. Around Shanghai, home to 40 million people. The area around Calcutta, 60 million. Here's Manhattan. The World Trade Center Memorial would be underwater. Think of the impact of a couple 100,000 refugees, and then imagine 100 million. We have to act together to solve this global crisis. Our ability to live is what is at stake.
Okay. So yeah, so we just have one planet, and this is the truth. This is happening, and this is no regular movie. This is a documentary movie. It's an old movie. It came out in 2006, and U.S. ex-Vice President Mr. Al Gore was the one who kind of gave talks and raised environmental awareness, and that kind of re-engineered the whole environmental campaign that, you know, global warming is real and it's happening. So for his efforts, he, along with the Intergovernmental Panel of Climate Change, IPCC, was given a Nobel Prize in 2007. So this is a great movie based on, you know, real facts, and you should really watch it. I think it's on YouTube. It's a documentary short movie. So I'll start. So this has given me a good sort of context of what I'm going to talk about. Everybody knows about climate change. We also do know about global warming. So now, before I start, so let me just ask you to look out of your windows. How is the weather like? I mean, we are joining from all over the country. Right now, where I am in Delhi, it's really sunny. Like, it's Saturday afternoon, 2 a.m., about 37 degrees, really hot. And, you know, there could be places where there must be like some sort of convection clouds or some rain. I doubt on the Indian subcontinent at the moment, but, you know, it won't be stormy or snowy at the moment for sure. But then what these terms are, they are weather. And when I say it's really hot, is it hot weather or hot climate? That is something we should understand. Now, when we talk about climate change, we talk about climate. And when we say it's how is the weather today or tomorrow, or let's say in a week, it's more of a weather. So what weather is short-term state of the atmosphere. So whatever the processes that are playing in, that is weather. So it can change within days. It can change within a day. So in the morning, for example, there was sun, and it could happen that, you know, in the afternoon you might get rain. So the weather is changing. But then when you talk about climate change, it's a long-term average of the weather that you kind of face over years. So it's like average weather over many years on a specific place. So when I look at the globe, or when I look at all the countries, the map that has just appeared has different colors. Now each colors correspond to a kind of climate, and it's called the Köppen climate classification of the world. So for example, you see yellow shade here. Now, yellow shade is associated with all the dry regions in the world. So you see Arabia, Northern Africa, and also parts of Thar Desert here. So this is sort of characterized as dry climate. Similarly, you also have tropical sort of climate, which get more rainfall, forests, evergreen forests, tropical forests, and they are around, like, located around equator. So, when we talk about climate change, we're talking about something that will be, that is kind of not normal, that would be abnormal from these sort of conditions. So, for example, where there's dry condition, it might not be dry, or where we have tropical forests or tropical rainfall, it may increase or decrease with time. So that is what is climate change on longer term. Now, so, of course, I mean, if it's hot, I came to office to give this talk, I had my umbrella on. So if it's a good idea to keep a track on weather, like, if it's going to rain, I take my umbrella. But then if it's even a better idea to kind of know how climate has changed in the past and how it will change in the future, of course, because of the reasons that were shown in the documentary trailer that I showed, but also I'll just talk about why. Now, a little bit on the climate change and global warming. So, when you say global warming, it's not always a bad thing. It is a good thing. And it is why our Earth is actually inhabitable. So if there was no global warming is more sort of, it's like a blanket on Earth. So if it was not there, Earth's temperature of average temperature of 15 degrees centigrade would not have been maintained. And, polar ice would have kind of covered much of the northern part of Earth. So what exactly is global warming quickly? So natural greenhouse effect, which kind of makes Earth habitable, is this, that you have these gases, carbon dioxide, nitrous oxide, methane in the atmosphere, Earth's atmosphere. These are called the greenhouse gases, which cause the greenhouse effect. So what they do is they kind of absorb the radiation which is being re-radiated by the Earth's surface, and these they absorb it, and because of the vibration in it, they kind of make the Earth atmosphere warmer. Now, because these gases, the natural concentration is being increased by humans specifically after Industrial Revolution. So now the balance is sort of skewed, and we have carbon dioxide, methane, and nitrous oxide accumulating in the Earth's atmosphere, and they are kind of absorbing more and more heat. Excuse me. And because of this heat, Earth blanket is getting thicker and thicker. And this blanket, which is getting thicker and thicker, it's causing the average temperature of Earth to increase. And this is something what we call as global warming. Now, where does the CO2 come from? CO2 comes from the fossil fuel burning. So basically, whatever older, like, animals and life that kind of died and got deposited under the Earth, over the time they decayed and formed fossil fuels. And when we burn them to generate electricity and power our daily lives, we generate carbon dioxide. So it comes from oil and coal. Now, methane is another greenhouse gas, mainly comes from cattle and fertilizers. And then there is CFCs and haloalkanes. So your ACs and fridges have these gases, and they also contribute to warming of the Earth. Now, also there is nitrous oxide coming from gasoline and agriculture, which is again one of the contributors. Now, there's also water vapor, which is like the most abundant greenhouse gas. But that it's sort of in a positive feedback that the warmer the Earth is, more water gets evaporated, and the more warm it does to Earth. So warmth it gives back to Earth. So there's also a water vapor, which is one of the greenhouse gases. Now, so what are the impacts of future climate change? Like, we know the warming is happening. One thing clearly, ice will melt. We know the polar ice sheet will melt. There would be increased forest fires because of increasing temperatures. Also increased intense flooding. That is because of monsoon and rainfall changes in places where it's not expected. And also drought conditions where, so for example, in fragile regions where the rainfall is very critical, it might face drought in future. And then heat waves is like commonly, like even in Antarctica, the temperatures are presently soaring high. So, these are in news really. So, these are all the impacts that we see physically of future warming. Now, what are the indicators of a warming world? Now, these are some of the indicators. So yes, temperatures, because of the temperatures increasing, we'll have sea. Yeah, so we'll have glacier melting. We'll also have sea level rising because of all the polar ice that is melted and gone into the sea. And because of increase in temperature, seawater would also kind of expand. So both melting of the polar ice as well as expansion of water would contribute to the increase in the sea level. And because sea level is increasing, species would be migrating polewards and upwards. Tree lines would be migrating polewards and upwards. Snow cover, of course, is decreasing. Temperature over land. So these arrows are basically indicating the direction of impact that it will have. So humidity in regions increasing, temperature over land increasing, temperature over oceans increasing, air temperature near the surface increasing, sea surface temperature increasing, sea level, of course, like I explained, increasing. Ice sheets decreasing and sea ice also decreasing. So this is what are the indicators of a warming world, and this is happening now. Now, do we know that, I mean, we did talk about that climate has been changing over the past. So quickly, one something, so this is what you see, the wiggles that you see on your screen is actually CO2. So here on y-axis, we have carbon dioxide, and on x-axis is the timeline. So how it has been increasing with time. So we have come in the 20th century, and it's the 1960, 70, 80, and you can see these wiggles. And what is interesting to note that, you know, the frequency of measurements that are taken are really high because of the instrumental record. Now, if we compare it to the past, there we are now in 2021, 2022. So 2021, we are here at 417 ppm of CO2. But in the past, like 800,000 years, CO2 was never this high. There have been changes in CO2, but, you know, on y-axis, you can see it's only between, let's say, 260 to about 190 ppm. So this is definitely not the natural climate variability. Natural climate variability was a period when, you know, when there were no humans. So it was here when the humans arrived, and after the Industrial Revolution that the CO2 started to peak, and currently it's like last year it was 417. And if I can go back to the slide, yeah. So I just checked it today as we speak on April 20. Oh, it's 21st, so it's 23rd today. But anyway, it won't be much different from what is listed here. So last year on April 20, 2021, it was 417.12 ppm. And within a year, it has changed 2 ppm. So this year, like 2 days back, it was 420.47 ppm. So that's about 0.8 parallel change. So that is just 1 year change. And, you know, we were talking about hundreds of years, and like, can you imagine what will happen after 50 years? And this looks like a very small change, but the impact that it exerts, this is really high. So, you know, now scientists are trying to understand like what will happen in the let's say 50 years, 100 years, 250 years. So what you see here is a plot which is one of the US scientist, Jessica Tierney. It's a very popular paper these days that came out in the scientific journal Science. And I lost my cursor somewhere. Yeah, so it's here. So this year is 1950. And what I showed is 2022 would be somewhere here, like just before 2050, somewhere in the middle. And if you correspond what the CO2 right now is, it would be somewhere around 417 or 420 ppm, somewhere here. But if you go back in time, now on x-axis we have time, and on y-axis again we have CO2. So if we go back in time, we have had time periods on millions of years when the CO2 was even higher. So for example, here, look at this red part here, red and orangish part. These were the times when CO2 was even higher on Earth. And if you go further back in time, there were periods when CO2 was again even higher. So, you know, 100 million years, for example. Now, you know, we scientists use model simulations to understand if the rate of emissions that we have right now, by emission, I mean the carbon dioxide that's being emitted by fossil fuel burning and, you know, other emissions from other sources. If the rate of emission continues to be like this, where will we go? So we have the middle road. Like if we kind of continue and look at the middle pathway, we'll go like that. So it's kind of will flatten out. The CO2 concentration will flatten out after a bit, but still will be definitely more than what it is today. So it will go up and then flatten out if we kind of put some sort of control on the carbon dioxide that is being emitted by us. Now, if we look at a sustainable pathway, like, looking at using more sort of sustainable ways of living, like, using cutting down on fossil fuel burning, using electric vehicles and, using solar panels and stuff, alternative sources of energy, there could be a way where we can kind of bring down the CO2 level on Earth. Now, but if we continue like this on the rate that we are going, so from 1950s where we are going, you could see that by 2250, CO2 would go up to 2000 ppm. And I don't even want to imagine what will happen when the CO2 would go 22,000 ppm. I'll show you the scenarios. If it goes if it is like there's a 1 degree change or 1.5 degree change, what changes we would have in sea level and other variables. So this is what we know. This is what we know about future. This is also what we know about past, that in the past there were intervals when the CO2 was higher than what it is today. Now the question comes, how do we know that the CO2 was so high in the past? Now there's something called archives. What you see in the pictures are like archives of normal life that is being recorded, but these archives actually are not like that. They are natural climate experiments. So by experiments, I mean some of the variables of climate were changed. So for example, if you change rainfall, there were things recorded, that information of changing rainfall was recorded in these archives. Now, what are these archives? These archives are this. So I've not labeled them here because in the next slide, I'll show you these archives and what sort of time scale you can use these archives. But I can just tell you quickly. So this is more of an instrumental archive where people would note down. So today, and it was the rainfall was this much of centimeters. Tomorrow it was now this is again goes back only up to historical times when people got interested in type of rainfall and the temperatures. So definitely a very good archive. This is a tree ring. So when you cut the tree like that, you have rings of growth, and that can serve as an archive as well. All these archives are storing information of climate. And these are cave deposits, stalagmite and stalactite. So these also can serve as an archive. Now, what do they record? So they record something called proxy data, which is basically the physical characteristics of the environment. So things like precipitation, rainfall, and temperature, changes in precipitation, changes in rainfall would be preserved in these archives. And the whole study of looking at past climate. Now, first of all, when we study past climate, it's called paleoclimatology. And now this brings us to the question, why are we studying past climate? I may go back to my previous slide quickly and show you that to know that previously when there were times when the CO2 was higher and humans were not there, how did the Earth respond to this kind of natural climate variability? We know that in future CO2 might reach that kind of level. So we at least need some sort of boundary condition or how Earth would react to natural climate variability. So we need to know how Earth reacted in the past, and then we can use that information to predict how it will be reacting or reacting in the future. And of course, we would put constraints like whatever anthropogenic inputs will be there. We can put that and understand the future climate and kind of prepare ourselves for future. So that is why we need to understand past climates. So so the study is called paleoclimatology, and this is what I'll be talking about today. Now, coming back to the archives, let's start from here. So this is 2022, somewhere here. We need to go back in time. These are instrumental records. So again, this only goes to mid 19th century, so 1850s, when with the advent of instruments and satellites, where you can we started measuring data like temperatures, rainfall at various places. So this is So this only goes back to 1850s. Beyond that, we do not have any information. There were no instruments, but there were historical documents. So people in the polls, like they would note down that this was the era when the lake froze, for example. Little Ice Age, for example, is one of the periods that happened in 18th century. So that was a time where people would write and document these kind of abrupt changes. So that is one measure. But again, these are very qualitative and they do not go much beyond. Now, if you want to go further back in time, we use tree rings. Now, tree rings, the way they grow and accumulate their growth rings, that is an indicator of how much water was there, and you can reconstruct past temperatures because of what temperatures these trees were going in, and also rainfall. So you can reconstruct that. Now, if you want to go further back in time, now again, x-axis, we still have years. So let's say 15,000 years to 100,000 years, you can go to lakes. Now, what do lakes have? Lake sediments. So the way lake, at the bottom of the lake, the sediments are deposited layer by layer. Each layer holds information. And if you look at 1 centimeter of that layer, that would have a climate information of whatever period that centimeter of lake sediment is recording. Now, you could also use coral reefs. So coral reefs can be used either the chemistry of coral carbonate can be used, or you can use the bleaching and non-bleaching if the temperatures were too high or there was no sunlight. Corals would get bleached out and die. So all these information you can use for reconstruction of past climate. Now, speleothem are cave deposits. So regions where there are carbonate caves, these deposits can be used as past recorders of climate. Now, one of the most interesting and very useful archive is ice cores. So there are certain reasons why this is important. One, it can go up to 1 million or even millions of years. Now, why is that? And is that when the ice forms, it traps air molecules. So that air that it traps, it has molecules of carbon dioxide. So if you can measure the carbon dioxide level in that air that has been trapped in the ice when it was forming, you can actually just get the actual value, what was the carbon dioxide like in the past. So, when I was showing you that Wiggles, which was going in, that carbon dioxide was reconstructed using these ice cores that have been taken from Antarctica and, polar north. So ice cores are really important. Now, one of the other reasons these are important is that they are relatively untouched. So there's no human intervention. They're not much yet. So they're they're well preserved. So and go further back in time. So real climate information, quantitative, and further back, well preserved. So now these are the archives that can be used. What I'll be talking today would be mostly on lake sediments because of the time constraint. I'll be talking about lake sediments and also marine sediments and how they can be used as archives of climate history. Now, how does it work? So let's imagine that this is a small ocean basin and there are shells living on the ocean surface, sea surface. So you can see this can also apply to lakes. If it's a small lake, there could be snails, garden snails living on the littoral zone on the sides here, or in the open ocean, there could be there are shells which are living on the surface as well as at the bottom of the earth. Now, when I say shells, these are organisms. These are mostly foraminifera, which are single cell organism from the group Protistans. But let's just say shells for now, and then I'll talk about in detail what forams are and how they're used. So, these shells are living here, and the shells are made up of calcium carbonate. So let's say, there's precipitation, there's rainfall event. This water will change the waters, whatever water is here. Now this water would mix in with this water body and would change the kind of, characteristic of this water. Now this is also impacted by whatever surface runoff that will come from the land and the chemistry of this water. And then evaporation would take out some water that would in turn impact the chemistry of this water. Now, when these shells die, they get deposited on the ocean bottom. And again, when another set of these animals die, the shells get deposited on the bottom of the oceans or lakes. Now, these layers get deposited in the sediments of lakes and oceans over time. So as they're depositing, they're recording some information, basically the water chemistry in which they were living in. So these organisms, when they build their shells, they take up, all sort of elements from, so these are calcium carbonate, so basically calcium and carbon and oxygen, CaCO3 from the water. And now I'll tell you how it will be different when you go back in time, but the chemistry changes with time, and the way they deposit, they kind of record the information layer by layer, and you can access them. Now, in reality, these shells look something like this. Quite big, huh? No, these are really, really tiny. So can you see this needle? And this is the needle hole. So those are the shells that I just showed, and they are that small. So like, nanometers, really, really small. Like, yeah, that's a typical G. Ruger that we use. It's a typical shell that I use for climate reconstruction. Now, okay, good. We did talk about ocean bottom sediments, but how do we reach there? So there is a consortium of international ocean drilling program where most of the countries, they contribute funds, and there are research vessels. They go out in the ocean, middle of the oceans, and choose sites to drill cores. So sediment cores from the bottom of the earth are drilled. And I just want to show you a video how this works. So, we scientists spent months in the ocean drilling these cores and bringing them back to the
The main purpose of the JOIDES resolution is to drill into the ocean floor and bring up sediment cores for scientists to study. These sediment cores can give us a lot of information about the Earth. Many pieces of pipe are put together under the derrick on the rig floor string. The crew Once the drill string reaches the ocean floor, coring begins. A long cylinder of plastic called a core barrel is lowered through the drill string, and the sediment cores are collected inside it as the drill string rotates. The core barrel is then pulled up to the ship through the drill pipe and onto the rig floor, where the technicians and crew collect it and begin to prepare it to be examined by the scientists.
So that's how the cores are brought on the ship. And then we split the core into half. And there you can see, as you go down like that, you can see that the sediments have layers of different colors and which the chemistry of those reflect the changes in the water chemistry at that time. Now, if there's no lake, or if there's no water in the lake, or we're not talking about oceans, if there is a dried lake, we can also kind of get a trench dug, and using a JCB or a normal digger, can kind of sample every centimeters of these sediments, and then take out shells out of them and do the chemistry of those shells, which would reflect the climate variables like temperature and precipitation. So yeah, now coming back to the chemistry. So getting the samples in the lab, looking at these shells. Now these are all carbonate shells. And like I said, these foraminifera are single cell organism protists, and these are all made up of carbonate. So calcium here, carbon with a covalent bond, oxygen, and carbonate ion. Now what happens is this oxygen here in calcium carbonate comes from water, and waters are really different in water. I mean, although they look, it's just water, but then oxygen can be either in the form of O18 or O16. So the isotopic signals are different, and isotopic signals get recorded in these calcium carbonate. Now, a little bit on the isotopic fractionation that I was talking about. So we know that oxygen has 3 isotopes. So when we say isotope, it has different neutrons. So where neutrons really vary between each. So when it's O16, it has a mass of about 15.99, and the difference is this 1 neutron. From O17. So O17 has about 9 neutrons, and similarly, the heaviest one is O18, which is a mass of about 17.99, and it has 10 neutrons, and same in, so these are the 3 isotopes. But now these are stable isotopes, so no decay. But But what is important to see is the relative abundance. So O16 is the most abundant one with 99.76%. And the next abundant one is O18. So it is about 0.2% of the total oxygen that is there. So we know that different isotopes of oxygen are existing in nature. Now, what happens is that the water that forms, so sometimes it takes O18 and sometimes it takes O16. So when there is a water body, it has both O16 and O18. And if we look at the masses, O18, water with O18 would be heavier than waters with O16. Now, because of this mass differences, there are physical processes like diffusion, precipitation, evaporation, freezing. All these processes introduces a mass fractionation. So now it happens because they have the same kinetic energy, but because of the difference in masses, the way they move from one phase to another. So, for example, water to liquid, or that really depends on the masses, and the velocity is like inversely proportional to the masses. So that's why they kind of fractionate during these processes. So if you look at the picture here, there is liquid rain that is coming out from clouds. Now, it's going from the clouds to the land. Now, waters with heavier oxygen isotope, O18, would fall out first as compared to O16. Now, similarly, during evaporation, water with lighter isotope with O16 would evaporate first. So lighter water isotope would evaporate more readily. Now, this introduces a fractionation in the remnant water body. So because lighter have already evaporated, it kind of gets enriched. So enriched in heavier isotope, O18. So in the water body, the isotopic signature of water really changes, and which is what is recorded in these shells. So, let us look at a warm climate, for example. Like now, again, we are talking about past. So, for example, this is a water body, and it has both heavy with O18 and lighter with O16 waters. Now, if it's really warm, both O18 and O16 would kind of evaporate in the process of evaporation because it's really warm. They get enough kinetic energies. Even the heavier ones get enough kinetic energies to evaporate because O16 would anyway evaporate. They have the sufficient kinetic energy, but if it's really warm, O16 also gets evaporated. Now, again, there's this fractionation that is being introduced in the water body that remains. So water now has a specific signature of isotopes. Now, this specific signature gets recorded in the shells that I was showing. So when these marine organisms form their carbonate homes, carbonate shells, they record this signature. So this could be any slice of time. So for example, now when it's warm, these shells are busy recording this water isotope signature that I'm talking about. So this get recorded, and when they die, they kind of settle at the bottom, and then you can access them in the way that I showed. Now, during colder climate, for example, the lighter, there's still water evaporation that is happening, but it's only the lighter ones that evaporate preferentially as compared to O18. Now, again, this is fractionation happens. So water now is relatively enriched in heavier isotopes, which have not gotten enough energy to cross this phase. And therefore, so you can see that heavier isotopes remain in water, excuse me, again, gets recorded in the isotopic, in these shells. So as a rule of thumb, you can say that heavier oxygen isotope values are in this water body, or in turn in the shells. When they are recording heavy oxygen isotope values, it means lighter have evaporated and the conditions were cold and dry. So this is like back calculating. So if we measure the isotopic signal in these shells and see what was the isotopic, and this is again relative to a standard. So, and if we see that they are relatively heavier, that means these heavier values means that it was cold and dry period, that whatever time that they are recording. Now, how do we measure them? Now, because these are microscopic shells, we bring them in the lab. We look at them and observe if they're well preserved or not under a microscope. It then, like the clean ones, then we go sort of a chemical treatment before going into the mass spectrometer. Now, quickly about the basics of mass spectrometer. These carbonate shells are acidified using phosphoric acid. carbon dioxide is released. Carbon dioxide goes into the mass spectrometer after a bit of going through the gas column to kind of remove other impurities. And then it goes through this accelerator plate, goes in this magnet. Now, this magnet, now there's also an ion beam which kind of gives a charge to these carbon and oxygen elements. When they get charged, they go through this magnetic field, and the deflection is basically dependent upon the mass by charge. So something with a higher mass would deflect less as compared to the lighter one. So we get isotopic deflections, and then in the detector, we can see how much, so we can see both. What is the elemental isotope in terms of what the mass is, and we can also see the abundance. So how much was O18 and how much was O16. Now again, this is relative to a standard, and this is how it looks like. This is the mass spectrometer that we typically use for measuring oxygen isotopes. Now we can also do carbon isotope because it's carbon dioxide is emitted like when these shells calcium carbonate is dissolved. But I'm for the time constraint, I'll just talk about oxygen isotopes, which is mostly very popularly used for climate reconstruction. So yes, that actually brings me to the first half of the talk. And then now I'll talk about the history and how we use this information that we talked about. So I'll take a couple of, or maybe a few questions before we go on to the next rest of the talk. So I'll see the questions that I have. Okay, so students can also raise their hands if they have burning question that they would like me to answer. But in the meanwhile, I'll just take one question that is here. So how is climate change affecting us at present? Ma'am, what is archive? Is it a job or a book? Excuse me. Okay, so first I'll take the first question, which is how is climate change affecting us at present? Now, you know, it really depends on where you're living. So for example, if you're living in Calcutta and you relatives living on the coastlines, they would have seen, and really old ones, if you go and talk to your grandmother or great grandmother, they would have seen with time the sea level or the coastal properties, the coastal ecology has been changing with time. Now, this is something you would not see because we have relatively shorter, time frame. So, but then when you turn, by the time you'll be 50 or you'll be 60, 70, that's when you'd be able to know that, it didn't used to be that hot. So for example, I remember when I was a school student, schools, going to school was okay. Like I didn't feel that hot, but now I can feel the temperatures changing. I can see that Northern India does face heat waves, and so that is how you see, because it's difficult to say in a period of like 5 years, unless you're measuring it, unless you're measuring carbon dioxide, that how it has changed. But then if you look at like 10 years, you definitely be seeing. And if you're looking at fragile regions like coasts of Calcutta, or increasing Australian wildfires, for example, it's one of the examples, and the hurricanes that keep coming in Northern America because of differential heating of oceans and heat being absorbed by the ocean. So all these are kind of so it depends on where you are on Earth that you would see that you would see these climate change. Now, what is an archive, and is it it's a job or a book? Okay, I showed the books to kind of give you a visualization of what's an archive is. So usually archive is something, it's like recording information. So it's physically, it's sort of a book. It is any physical thing which records information. So, for example, historians go to library and look at archives of past how past history has changed, and so those are archives also, physical books and letters and newspapers. But for a climate archive, we look at the things like lake sediments, ice cores, speleothems, and tree rings. All these have information recorded about past climate. So yeah, so in terms of climate, that's a climate archive. So it's not a job, it is a physical thing which records information of past climate. Now, again, this is a question by, is climate change because of hole in ozone layer? Now, that is a very interesting question. So we know that, ozone, now there's no hole as such in ozone layer. It's not like, on top of Greenland, there's a hole and Greenland ice is melting because of that hole. No, it's the overall concentration of ozone that has been decreasing because of we releasing chlorofluorocarbons and chlorofluorocarbons reacting to it, and ozone being decomposed to oxygen and free radicals. So yes, ozone does contribute to the whole, decrease in ozone does contribute to the whole global warming, because it forms a blanket which kind of reflects back the solar radiation coming in on Earth. But a decrease in ozone is not the only reason of climate change. Like I said, increase in greenhouse gases because of us. So is one of the major reasons of global warming, and because of global warming, the changes in climate that we are seeing. How we got various types of side effects while weather or climate changing. Normally, we say because of cold and hot changing in temperature affect us for fever, common cold. I didn't really understand this question. How we got various types of side effects while weather or climate changing. Normally, we say because of cold and hot changing in. Okay, I think what the student here means is changing seasons. So changing seasons is something that is normal. That is because of where you are on Earth. So for tropical countries like India, because of the revolution of Earth and rotation of Earth, you would Earth's orbit, you would know that Earth would have, out of the 12 months that we have, there would be seasons that these tropical, that the countries in these latitudes would have seasons. Now, and then, so, in cold season, so in the northern hemisphere, it's during the November, December, January, that's like the typical cold season, and we get common cold and fever that you're saying. But in the southern hemisphere, at that time, it's summer season. So it's relative where you are on the globe. So it's not that climate change is not that. What you're talking about is seasons, and it's normal to have seasons because of where you are on the globe. But climate change is something longer term. Like I said, weather is one day, season is because of the orbit, Earth's orbit and orbit parameter or vital parameters. But climate change is all this is happening. So seasons may get really intense. So it might get really cold or really hot. So that might be because of the changes in climate. But having seasons is normal. So is there any more reasons for changing in climate? Yeah, I mean, there are several. Like I said, most of it is because of why it is warming, how it is warming, and then rest are impacts of warming. So yeah. Okay. So, ma'am, as you said, if climate is warm, the water isotopes of water will work as recorded information. Considering amount of O16 and O18 water molecules are evaporated, but how carbonates are giving us recorded information. Yes. So I'll just quickly go back to the slide. So when these carbonates are formed, yeah. So these carbonate, when they are forming in these shells, first of all, these shells which are made up of carbonate are forming in water. So where they are getting their oxygen isotope or oxygen in this CaCO3, the oxygen that is coming in this molecule is from the water in which they are living in. So if there is a change in isotope, be it 16 or 18, they would take that whatever isotopic signature that is there of the water in which they are living in, they would take it in and they would record it. So that's how they get it. Okay. Is climate change will affect Earth livelihood rotation? Okay, this question has actually several parts. This will be the last question that I would take, and I'll take the rest of the questions in the end, because there's quite a few interesting slides that you would want to see before we go into more questions. So yeah, the question is climate change, will climate change affect Earth livelihood rotation, or effect on Earth's orbit? So it's the other way around. So yes, climate change would of course, affect the livelihood, like I said, because of the extreme events that happen, forest fires, hurricanes, storms, rainfall anomaly, like somewhere it's drought, somewhere it's like, which is something which is not normal. So that will happen because of changes in ocean circulation, ocean heat, the amount of heat that is there in the atmosphere, that is changing, ocean heat is changing. So everything is being skewed from normal. Now, it will impact the livelihood, of course. You go watch this movie that I was talking about, the documentary movie. It would show that how coastal population are being kind of displaced because of sea level rising, so livelihood does get affected because of millions of refugees are will be generated because of this displacement. So yes, livelihood does get affected. India, for example, it depends heavily on Indian monsoon rainfall. And because of changes in atmosphere, which is an integral part of the whole monsoon system, monsoon brings in moisture from the ocean to the land. Because of changes in temperatures, monsoon would be impacted really badly, and the rainfall would change in coming times. And if the rainfall would change, the agrarian society, because India is basically agriculture-based society, so that would change. A slight change in rainfall would change the agriculture production, and then Indian economy would suffer. So yes, the livelihood definitely is impacted. Now, rotation on Earth and what is the effect of Earth? I didn't want to go in that detail but then that's a very good question. So when I was when I was showing all the figures, like how carbon dioxide is changing in the past, what do you think kind of made those changes? What led to those changes? It was the Earth distance from the sun. So it was too close, it was really hot. And if it was too far, it was really cold. Now, what changed this distance was the Earth's orbital geometry. So Earth's orbital geometry has been changing, and it changes because of the the gravitational pull that is being applied by other planets and other universes. So again, I'm not going into that detail. That is a different story. But when we talk about longer term, but it works on really long term, millions of years. So when we talk about longer term climate change, we need to put that into consideration. What was the Earth's geometry like? Was it closer to the sun, or was it further apart from where it is presently? But when we look at short term, we look at seasons, we look at last 10 years, 50 years, we look at various other factors that are responsible. So I'll just stop here with the questions, and let's go back to where we are. Yeah, where we were in terms of, sorry, I went back further. Yeah. Okay. I didn't put a poll here, but it would be interesting to see how many of you can kind of recognize what you see on your screens. So on the leftmost, you see some beautiful pyramids. In the middle, you see some other sort of older kings and queens and whatnot. And on the rightmost, you see the famous cart and the dancing lady, and also the urn and Shiva and unicorn. Now, all of these are artifacts and structures belong to one of the ancient civilizations. So, I mean, if there was a poll, I would have asked you to guess, but I'll just tell you the answer. The first one are the Egyptian pyramids. So you might have heard of Cleopatra, the queen, and these are the pyramids in Egypt that are there. These pictures and these structures, these sculptures and artifacts belong to Mesopotamia civilization, and this one is closer to us, somewhere on the borders of present-day India and Pakistan, in northwest India. Now these are from what is called as the Indus Valley civilization, and it is also called the Harappan civilization or the Mohenjo-daro civilization. So what is common in all these civilizations is that they kind of sprouted out, or they began in various regions of the world, but around the same time. So these are also called the Bronze Age civilization. So this Bronze Age was sometime between 3,000 and 5,000 years back in time. Now, geographically, if you see, so here is India, and in yellow is Indus Valley civilization, and here Mesopotamia civilization is here, and Egyptian civilization. So all the Indus River would have Indus civilization, Tigris, Euphrates, Mesopotamia, and Egypt is here on the river Nile. So And so yeah, so these are Bronze Age civilization, and these are really complex ancient agriculture-based civilization, and roughly about 5,000 and 3,000 years ago. Now, what happened is that at some point these civilization did not continue, and they kind of collapsed. They left their homes. They people left their homes. They went somewhere else. So whole city concept. They abandoned their cities. They went on to form villages, really small settlements all over the place, but left the region altogether. And this happened sometime around 4,200 years ago. So interestingly, like, why did they leave their very well settled life? And there were trades from India to Mesopotamia, and why did they leave their settled life? So that is a question. So so in this, the cultural change that happened between 4,200 and 3,900 years ago, what is the evidence of this decline? Now, the evidence is in the form of that, weights system. They had proper weight system that started disappearing. There was no trade. Writing began to disappear. My laptop has some problem. Okay, so urban cities were again abandoned, and they were mostly formed. They again went back to other regions, neighboring regions, and started forming villages. There were more diseases, and they started moving, like I said, moving eastwards. Agricultural shift were there. They were mostly, looking at either summer or winter crop. So they were like, distinct shift. In my screen again, I think.
Sure, no problem.
Tommy, I'll just. So the thing is, so something happened in these civilization, and around 4,200 years ago, that there were several cultural sort of changes, and when people started moving away from the cities. Now, there are several theories. There are theories like, there was some sort of invasion from other parts, and some say that because of the drier climate and fluvial shift. By fluvial, it means the rivers were shifting, so they had to move following the river or following where the rainfall was more. But recent paleoclimate research shows that yes, there was a drought, or kind of drying around that time, and because of the civilization tried, but for 200 years they could not cope up with the drying sort of climate, and then they started moving towards regions where they could find more rainfall, so they abandoned their whole urban life altogether. So this does not happen to Indus civilization. They happen to other civilizations that we were talking about. Now, if you look at the map on your left, this is map of Northwest India, and all the yellow dots that you see are archaeological sites. Now, these have been excavated by archaeologists. Now, this maps come from University of Cambridge. So, archaeologists at Cambridge, they've been working in Northwest India extensively and looking at all these sites. And they say that these sites, at some point, they were sites all around and even in the Thar Desert region. Now, what they really wanted to know was whether or not there was a climate change at the time when this shift happened, when the urban civilization collapsed. So I was a PhD student at that time. We went around looking for evidence. Now, what you see here on the top right picture, this is a Thar Desert. Sand dunes, as far as you can see, middle of nowhere, we found this mining going on. So this mining activity that was going on, they were mining it for gypsum. Gypsum is basically calcium sulfate, and this was under a sand dune. So gypsum can only precipitate out from water. So what is this? What are these gypsum? Huge, massive. This is 2 meters. Massive gypsum doing here, and that too under sand dune. And it's not like somebody has kept it here. It's not a small. It was really extensive, several hundred square kilometers. So that means this region had water at some point. So there was lake, and it was densely populated. Now, if we look at the location of this lake that I'm talking about, it's here. So all these lakes in red were surrounded by these Indus civilization, but right now this is what it is like on the top right. There are sand dunes, and there's no civilization, no vegetation. People don't live here. So let's look at one of the climate records that we use these sediments to reconstruct. So again, this is the climate record that I will show. It would not come from this lake in particular. It would be from the other lake, Kotla Dahar, but you would get the essence of what climate records can tell you. It is again very close to Rakhigari, this lake, one of the urban sites. And so these are the deposits that you see, and if you sample it from top to, so this is modern, and if you go down the section, you would go deeper and deeper in time. So we would sample it, we would take out the shells and do chemistry of the shells to reconstruct past rainfall. Now, this is a typical climate record. So all the wiggles, I'll just quickly explain. On the where you see weight percent carbonate, it's the measurement how much of carbonate is there in the sediment or the soil that you're looking at. So lake sediments in this context. So and as you go down, so if you imagine that this is the top x-axis, if you imagine this is the surface of the earth or surface of the lakes in which sand dunes are sitting at the moment. If you go down, you're going back in time. So by kilo year, it's thousands of years. So you're going 2,000 years time, 3,000 years, 4,000 years, because we are interested in sometime around 4,000 years. So that's why we kind of went back in time to look at how was the lake changes with time, like on thousands of years time scale. So this is weight percent carbonate, and in terms of how much it was like really less. Right now there's no carbonate, it's just dune, sand dune, no carbonate at all, no shell. And it was less for quite some time, like less than 10%. But just around after 4% of after around 4,000 years ago, after that it was really deep lake. There were shells like these. There were the carbonate content was 60%. And if you look at the oxygen isotope, if you remember the rule of thumb that I told you, that if it's really heavy, by heavy oxygen isotope value, I mean really positive, it's dry, and if it's really negative, it's wet. So you can see that sort of average values after whatever happened here are sort of dry, and average values here are wet. And these are the number of shells that were found. So these are three panels, three different kind of proxies, all pointing out towards the same thing. Now, if we quickly look at how the lake has evolved, so this is the deepest part of the lake. Now, how do we know it? It's because of the calcium carbonate content. If you look at how much it was about 60 to 80%, like, really high carbonate, really a lot of shells. Like these were the shells, a lot of shells. We would easily measure oxygen isotopes on these shells. The shells will look like this also, because this is a terrestrial archive. It's on land, and the oxygen isotope are really negative. So that means it was quite wetter at that point. Now, if we next phase was relatively drier. So if you look at the oxygen isotope, it's less negative now, relatively. The values are less negative, and calcium carbonate also is not that high. It's now less, somewhere around 40% average, and shells have also kind of decreased. Now, at some point around 4,000 years, there's a drastic shift in oxygen isotope. So you can see from like about -4 to +4. So it is from wet to sudden dry. So something happened around this time, that the isotopic concentration, isotopic abundance changed in the lake. So this is a lake. Lake water isotopic abundance completely changed. And the lake was getting water mostly from the rainfall, the summer rainfall in this region. So summer rainfall changed, which is why the isotopic signature of the lake changed, which is why the oxygen isotope that these shells took to make up their shells, that changed, and which were recorded. And when you kind of reconstruct this, you can see this drastic shift. After this point, there was no carbonate, relatively, like really less, only few shells that we could measure, and other shells were also absent. So clearly this was an abrupt drying that happened, like abrupt monsoon weakening that happened around 4,000 years ago. And again, this is coming evidence from here, so which is very close to all these civilization sites in the sites that we showed. So around 4,000 years ago only, most of the archaeologists, they gave me these two graphs, and what is interesting to see in these two maps is the location of these sites. So for example, between 4,500 and 3,900, there were really nice cities with trades with Mesopotamia, and all around Thar Desert, and even in on the margins of Thar Desert. And but just after 4,000 years ago, when the abrupt drying happened, all of these sites, there's no sites found here after that. All the sites have kind of migrated. They've left their homes and migrated towards the Ganga plains. So where there was more water. So this map really fits in with our story, with the climate record which we gave, that there was a monsoon rainfall weakening around 4,000 years ago. So clearly these now what impact they have, this civilization, these populations, in terms of agriculture because of the rainfall. So what ultimately contributed to this whole cultural change or moving is still being researched. Like how did that change in rainfall impacted their life is being looked after. But this evidence that there was a weakening of monsoon in itself is a really it's a really starting point to understand how past civilization reacted to climate change at on those time scales. So like I said, it's not a one like it's not location specific. It is not just from one location. It is not from region, just this region. This is from the tropical belt and all the three civilization, Egyptian, Mesopotamia, and Indus Valley. Around 4,200 years ago, there were like really drastic changes, cultural changes in these civilization that was noticed. And there are paleoclimate records from those regions, from Egypt, from Mesopotamia, also isotopic records, and they all point towards that there was something happening around 4,200 years, that the whole global climate did change. So we know this from the past climate records that we generated. Anyway, so this was about ancient climate, ancient civilization. So now what about the future climate? So we know, like we said, we know that the climate is changing. And so there is this intergovernmental panel of climate change. Now this is a UN organization. Initially it was started by World Meteorological Organization and UNEP program, but now it is also endorsed and taken by the United Nations. Now this consists, so this is not a political organization. It consists of scientists from all over the world who provide sort of scientific evidence of changes, and also model how the climate is going to change in future using various variables, and that we have. So they kind of publish reports. So the recent reports is the recent assessment report in 2021, and then this is the sixth assessment report. So they've been publishing. Now if I can remind you again that IPCC was the one that got Nobel Prize in 2007 with Al Gore. So Al Gore was the ex-US president who made that movie, and was like an environment campaigner, raising environmental awareness. So this organization also got Nobel Prize. Now the physical science basis, again, several scientists, even from my center here, Center for Atmospheric Sciences, their scientists are involved, and they've contributed to this report in terms of how like this region of the globe has reacted to changes in climate, and how it could react to future changes in climate. So if you look at the general sort of report highlights, it is that the CO2 concentration is highest in the last 2 million years right now. Sea level rise, the rate of sea level rise is the fastest at the moment in the last 3,000 years, and Arctic sea ice also is lowest. And similarly, glaciers are also retreating at an unprecedented rate. So if we continue to do this, if we continue to emit CO2 like this, CO2 increase, other greenhouse gases increase in the atmosphere like this, we can say that the sea levels are expected to rise about 10 centimeter higher by the end of this century. Now, by 10 centimeter, you can easily say that 10 million people would be displaced. They would be impacted by coastal flooding, including whole of America, whole of Manhattan, whole of Calcutta, or Bangladesh. A lot of the coastal regions from Bangladesh and Manhattan, for instance, would be underwater. Statue of Liberty would be underwater. So that 10 centimeter high sea level would impact in that way. So if under 2 degree, if we continue like this, so this would be under 2 degree warming than 1.5. So 2 degree of temperature would increase. That's when we would see this 10 centimeter rise in sea level. Now, now this is again x-axis. We have time and we have temperature difference on y-axis. Here you see in black. Here the black line basically tells us how the warming has happened in the past. So temperature, how has it changed over in the past up to 2,000 years, and beyond that, what if the aggressive emission is not reduced, and if it's business as usual. So whatever we are emitting, if we continue to emit like that, so basically we are going on that black graph, and we're increasing. Now these are all projected changes. So model simulations, we predict that we're going to change the temperatures like this. So we can easily see 4 degrees of changes. And here, when I was talking about 10 million people being displaced, it was just 2 degrees of warming. And this is just 2100, so not too further in time. But if we kind of reduce our emission and we control it, we can go to this what is called as like a standstill, and a kind of we can control it to less than 2 degrees of warming, and this is what is required. So just under 2 degrees warming would save a lot of people. So, but what do we have to do to keep this 1.5 degree centigrade of warming? We have to reduce the emissions drastically, up to 45%, and this has to be done like now. And the limit has been set to 2030. Now, the several of the countries have signed the Paris agreement that happened, and they've pledged that they would reduce the emissions. And also, we need to work on more renewable sources of energy, more sustainable way of living. Solar panels, wind energy, other renewable energies we'll have to depend on, and that has to increase by up to 70 to 80% by 2050. So this is something we need to do to avoid this climate catastrophe that we are nearing. So I'll end my talk today here, but then I'll just want to point out something that I started with. So what is my background? I started with chemistry. I use chemistry. I use physics to model the data, the chemical data that I get, and people do mathematical modeling to predict future climate that you were seeing, like what are the temperature rise, and so mathematics people with background in mathematics and engineering come here, they do this kind of modeling. Now what are the implications are also to understand, like apart from to understand what archaeological changes that have been in the past, climate science, yes, we would know how the climate would change. It has major implication on the public policy and how government would react to these kind of climate changes and impacts. And this is again region specific, different region would react differently. So this is now all this field is related to paleoclimatology, and it's an upcoming field. And yeah, so that's it. I would end my talk here and invite you to ask questions. Thank you. Okay, so I'll start with the questions. So the first question is, ma'am, will soil erosion lead to lesser atmospheric CO2 in future? Now, this is actually a very good question, whoever asked. So the reason why I'm saying it's a very good question is, when you say soil erosion, it is quite intertwined with climate change. So basically, CO2 in the atmosphere is taken up by plants, when and to make to basically synthesize photosynthesis and make their food. Now that is the way one way that we kind of remove CO2. So we have to plant more trees, to get remove CO2. Now, when there is soil erosion, you kind of removing more plants, and again, it has a positive feedback. So if you're removing more plants, there's more soil erosion because roots are not holding it. So it is quite tightly linked with the amount of CO2. But on longer time scale, if we see, CO2 is absorbed by some of the rocks, like carbonate, for instance. And so CO2 carbonate act as a CO2 reservoir. So they react with CO2, and they kind of so CO2 plus water, so weak carbonic acid that is formed, that kind of dissolves the carbonate rocks over time. And the water, so with rainfall, when CO2 reacts, it dissolves the carbonate rocks, and the water or the runoff goes into the sea. So CO2 is again being taken up by the rocks. Now, if there's more erosion, that means there's more CO2 being taken up, more rock is kind of weathering and eroding into soil and being weathered off. So it is again a very I cannot say if it will reduce. The question was if it will erosion would lead to lesser atmospheric CO2. It is difficult to say, but the more erosion is basically the erosion or weathering is takes up more CO2. So it kind of impacts the atmospheric CO2 concentration anyway. So so yeah, but what CO2 is mainly increasing by fossil fuel emission. So it would reduce the CO2, yes, but but it would be definitely on longer time scales. Now, how will methane as a greenhouse gas will affect the climate? In a similar way that they would absorb there is shortwave radiation coming from the sun. Some of it is reflected back from the atmosphere, ozone, and some of it is also reflected by the land surface, glacier surface, ice albedo. So if as long as it's reflected back, it's well and good. But then if it is reflecting back and gases like CO2 and methane, when they take it, they absorb the long wave that is being emitted back, and they kind of vibrate, and then they emit more energy, and that's how they kind of increases the temperature of the atmosphere. So the absorption of infrared rays and the vibration and the energy that they produce, that increases the atmosphere's temperature. Now, yeah. Okay. So, ma'am, what is radioisotopes? Okay, that's again. I mean, that you find it in your textbook. But when I talked about oxygen isotopes, I was talking about these are stable. Radioisotopes decay. So when there is a fusion, so they can decay by emitting one neutron. For example, when there is a fusion, there's a fusion reaction, they might decay. So they could be radioactive. So I mean, very simple example, like there could be radioactive radio isotope of carbon, so 14C. So over the time, it decays to C12. So, but when I said stable isotopes of oxygen, they would not decay in, yeah, they would not decay in the atmosphere. They're stable. So how are radioisotopes related to water? Um, um, yeah, like I mean, so it depends on which element you're talking about. Like I gave an example of carbon. Carbon is not present in water. Water is just H2O. So we're not talking about a radio. So radioisotope is not directly, it's not in the composition of water. I was talking about stable isotopes of oxygen, which is there in H2O. And yeah, I've been asked to take names also. So if you could tell me, yeah. So for example, Mayank, ma'am, these shells are transparent. Mayank, these shells could be transparent or could be opaque. So it depends on what is the crystal structure. We also, like, we also go into the detail of crystal, whether it's a carbonate form, aragonite, or is it calcite. So carbonate can exist in two forms. So so that would make you would know. So some of them are really transparent, and you can actually see the one-celled organisms under the microscope. You can see how they're living. But some of them are, opaque. Arnav, is our mythological text, there were references of drying of the Thar Desert. Do you think that happened due to climate change? Possibly, yes. Like I said, mythological text again is a kind of archive. So it's an archive which doesn't go hundreds and thousands of years back, but it only goes. So this is something I talked about when I said historical archive. So people would shruti and smriti, so they would listen and they would remember and they would write whenever they. So and when we go back to. When we refer to all our mythological texts and say, oh yeah, there was a sea there, and to the extent, I'll just tell you a small story that when I went to the lakes in Northwest India, really old people, like there was this really old grandfather sort of a figure who I found, and he was like some 100 years old and really hale and hearty talking, and he said, you know what, there used to be a sea here. And I said, how do you say that? All I see is a cropland, you're growing crops here. And he said, no, you dig 1 meter and you would find shells. So he knew there was water here, where now he's trying to grow some vegetables. I mean, it is on the border of Thar Desert. They're still trying to grow some vegetables. But what I mean to say is, like, all these things are historical records. So mythological texts are also an archive. And so, yeah, possibly if the timing coincide around, if it's roughly around the same time, possibly it could be due to climate change that happened. So, Mayank, ma'am, are there actual solutions that we must do to stop climate change? It's a very good question. We all have to contribute in our own manner. Like, by if we from bottom from it has to be at the ground level, actually. Like, for us, we can pool in cars. Like, if I go to send my daughter to school, I can pool in. I can get other students, other children who are going into the same school in the same car. Why emit so much? And why like we are stuck in traffic? Why? So carpooling is something we can do. For example, you can save electricity, something, and plant more trees. These are really small steps that go a long way if all of us do it. So yes, so that is one really small step. But the real solution has to come from politically, really come from countries. They have to come forward, move to other sources of renewable sources of energy, and move to sort of sustainable life and look for renewable energy. Governments have to put more money for fund research, which are kind of, based on, or which are focusing on renewable sources of energy, sustainable ways of life. and so on and so forth. So policymakers have to play a big role in that. So you cannot really stop it, but you can kind of impede it or slow it down by, checking on the carbon emissions that we are making. Yeah. So I don't see any question here at the moment, but so I'll just quickly take the chat box here and see. Very good question, Arnav Jakwal. So, ma'am, people are not too ready to mend their habits. 45% lesser emission by 2030 look difficult to reach. How do you bring the awareness? One way is like this. You are all school students, and I was really excited to talk to you, like young minds. And later on, like after you finish your school, you might go into engineering or science or whatever degrees, but you can work on such solutions, such problem. I mean, by 2030 there's still time, so it has to everyone has to chip in. Even one effort would count. So everyone has to chip in whatever they're doing. For example, I am a paleoclimate person. I reconstruct climate, and I try to understand how it has changed in the past, doing that. And also, just in my normal routine, I would like switch off the lights, cool car, and all that. So yeah. So this is something you can do from your end. So yeah, awareness is something that is really important. So is there any impacts of climate change on plant? Yes, I mean, of course, if the temperatures and rainfall will change. For example, for example, the whole Indus civilization moved or abandoned their urban cities because they could not grow plants, they could not grow their crops that they were eating. There was no rainfall. So that was like, that is something we have to learn. So if there are changing rainfall patterns or changing excuse me, rain, it has a huge impact on the crops and agriculture. So 1 year of famine causes many people depend on agriculture. So yes, so it impacts the plants severely. So this is from YouTube, ma'am. What is the reason of climate change earlier during Indus civilization? Very good question. Did not talk about this because of time constraint. So yes, so there was no industrial revolution. They were not emitting much of CO2. How did climate change back then? Indus Valley civilization or Mesopotamia? Very good question. So because when I was showing carbon dioxide changes in the past, how did they change? So they were changing because of the Earth's natural system. So there are processes, climate processes, which involves ocean circulation, how ocean currents move, and also atmospheric wind patterns. They change, and if they change, they impact the rainfall on the Indian subcontinent. So it is still unknown, but there's something called, I don't know if some of you might have read about it in schools in environmental sciences lectures, but there's something called El Nino Southern Oscillation, or El Nino. So that happens in the Pacific Ocean. So temperatures change. There's temperature changes in the Pacific Ocean, Eastern and Western Pacific Ocean. And now those temperature changes kind of induces a different atmospheric pressures, and there are warm centers that are created in the Indo-Pacific warm pool. Now those kind of anomalous changes directly impacts the atmospheric circulation that brings monsoon rainfall on the Indian subcontinent. So there are paleoclimate records from that region, from El Nino region, and they also say that there was El Nino event. And if there is an El Nino event, usually the monsoon weakens and the rainfall is less. So like reconstructions, paleoclimate records from that region say that around 4,000 years ago, during the Indus Valley civilization, there was like this a lot of every year there was an El Nino event which impacted the monsoon rainfall at that time. So we have to kind of join bits and pieces. So if we are looking at something as remote as or as far from India as Pacific Ocean, that can also impact the civilization on India. So that's why, I mean, one country or one city cannot do anything. It's a global awareness, global efforts that has to go into. Mayank is asking. Yes, ma'am, awareness is important. Just 2 days ago, I had my friends make a. Yes. Yeah. Okay. that's good, man. Good to know that you are trying to aware more people, and you uh, Christian Kumar Mishra is asking, ma'am, what is radiogenic radioisotopes? Again, I told, as I said, radioisotopes decay over time and they have a half-life of decay. So, for example, C14, which is what we use to date. So, for example, when I look at the layer of lake, or look at a shell to know what time it came from, we date them. We use radiocarbon to date them, because carbon in that calcium carbonate is carbon. It could also be one of the isotope called C14. So C12 and C13 are stable. C14 is radioactive. So radio would decay with time, and by using half-life, we would know what is the time of that shell. When was it living? 100 year, 1,000 year, 2,000, 3,000, or when it was living. And then we use oxygen isotope to make the record. So how radioisotopes are related to water? I mean, I've answered this question that H2O doesn't have any radioactive isotopes. Yeah, I heard of net zero emission. So net zero emission is basically this. So when I was showing this plot, that if it is business as usual, if we kind of continue to emit in the way burn fossil fuel in the way that we are emitting, we are going on the same rate, then it would really peak up. But if we have sustainable solutions coming to rescue, then that's when. So we cannot stop emission like altogether. Of course we cannot, because it is our world is run by fossil fuel burning. But if we can replace this fossil fuel energy by using sustainable forms of energy, 70 to 80% we can reach a stage called net zero. So even if it is emitting, it wouldn't impact because of the sustainable resources, that source of energy that we'll be using. So that would bring us to a net zero. Arna, ma'am, is there any way we can do dating, etc., and without sophistication machine? Without sophistication machine, it would be difficult. I cannot think of anything, but yeah, but you need a mass spectrometer to see how much of C14 is there and how much of it has decayed with time. So that will give you a day to associate with that change. Ma'am, this is Mayank Kumar Rajpur. Ma'am, you told someone that I didn't understand. You said archae. I said archaeology. So archaeology is a science, who study past changes in civilization and societies. Yeah, I think I've answered most of the, almost all the questions. Shomik, do we have any more questions on other platforms like YouTube?
No, I think these are all.
These are all the questions. Okay. Well then, yeah, we're done.
Okay, so thank you, Professor Dixit, for a fantastic talk, and I'm sure this, all of us now are enriched with more, details of climate change and how we can tackle it. And I'm sure this, our young minds, the kids would be really curious to know more about this and would like to say something from their end also. So we kind of decided one context. And what do you think about this? Let me explain it. So we would ask all the participants to think about the climate change issues and how we can tackle from their own perspective. And we would ask them to send us an email with their ideas. So we collect all the ideas and probably select a few of the best ones, and then and the names will be announced in our next Sci-Tech spin lecture. So what do you think about this idea?
Yeah, no, great. I mean, these are the young minds, and I'm sure they'll come up with. They're asking me solutions. I was about to say you should probably propose. We've been doing. Our mind is already kind of seasoned. So
yeah, so we can do this, and it would be nice. I mean, to know their stories and their thoughts on these things. So okay, so with this, let me thank you again, Professor Dixit, for this wonderful talk, and now let me thank the organizer or organizers. First of all, I thank Professor Pritha Chandra, who is a professor in the Department of HSS and Associated Dean Outreach Program, Professor Ravi, Professor Jay, Professor Rajendra, Professor Soumik Siddhanta, and Professor Divya Nair. and who are like a co-organizer of this event. And we have an amazing team, support team, Mr. Gaurav, Kuldeep, Renu, who worked tirelessly to make this event successful and run this program so smoothly. So big round of applause to them, and thank you guys. With this, we'd like to thank all the deans of our institute and our director, Professor Rangan Banerjee, for their support and encouragement. And special mention to various electronic and print media for circulating our program and helping to reach out larger audience. I think we are going to have many more lectures of this kind of lecture of this type under the Sci-Tech SPIN initiative. So stay tuned for the future announcement. And last but not the least, we'd like to thank all of you for your active participation and all the questions. I mean, they were super fantastic questions and very relevant to our daily life. So with this, I think we are almost at the end of this session, and so let's conclude it here. Again, Professor Dixit, thank you again.
Thank you.
And to all of you, please send your comments, your thoughts to our, I think you have our email address, outreach program email address. So send your whatever comes to your mind related to climate change. We'll be happy to receive your emails, your ideas, your thoughts. And then the best ones would be selected and displayed on the outreach program. And again, the names will be mentioned in the next lecture. So with this, thank you again. Thank you all and take care. So COVID is still not over. So take precautions, wear masks, and let's hope that we don't see any further wave. With this, take care and thank you all. Bye bye.
Thank you. Yeah. Bye.